Hello, this is Alan Folmsby speaking to you from Hawaii. This is Theoretical Physics live streaming. Today the subject is about radon. It's the pear-shaped nucleus of a inert gas. Last week I was talking about the neon, and now another inert gas is radon, but it has a half-life of only 4 days. You may have heard about it accumulating in people's basements, and that's kind of dangerous. So I'm going to just give you a little introduction on what today's about here. Hey, I'm back in the Theoretical Physics laboratory here. And this one is about radon and the experimental evidence that supports my theoretical physics. So you may have tried searching around the internet to find what is the structure of the nucleus of anything. Iron, radon, carbon. And a lot of people in the internet will tell you it's kind of round. These nuclei, like iron, they say, is almost round in the nucleus. And as an approximation, yes, if you think a square is like a circle, then in that sense, yeah, iron is kind of round. But really, as I've explained in the earlier lectures, this is more of a pyramid shaped on top of a cube. So the cube has 6 faces, so there's 6 little pyramids protecting all the cube from any kind of fission or fusion. So the experimental evidence comes from Europe. At CERN, there's a collider, and they had radioactive atoms or ions flying and colliding with things, and they're able to figure out the shape of the nucleus is like a pear shape. It's not round like a basketball. It's more of like a pear, where one end is bigger than the other. And that confirms what my theory independently has shown. Their experiment was done in 2013, but I didn't see it until after 2017, when I had predicted the shape of radon already. And radon is one of the inert elements, inert gases, which is on the right side of the periodic table. So I'm going to walk over there and we'll look at that briefly here. All right, now this blurry picture on YouTube video is the periodic table of nuclear structure. On the right-hand side are all those inert gases, and they are foundation elements, simple pyramidal cubes. But the other elements are incremental elements. So there is about 90 incremental elements that are built on the foundation elements. There's 18 foundation elements, such as oxygen, xenon, and all of the inert gases, plus iron and zirconium and cerium are also the foundation elements. And then I'm going to bring up a closer picture, though, of, in particular, the element radon. We see that it is element number 86. It has 86 protons. And in the silhouette here, we see that it's kind of pear-shaped, that at the top it's bigger than at the bottom. Now, if you blur this picture enough, you'd be able to see similar to what the experiment is going to show you in a minute. I'm going to go to the Nature magazine, and it's copyrighted, but under the fair use for educational and a scientific comparison. I'm going to show actual pictures from that paper, and I'm going to explain it very soon. So in that paper, the experimentalists have a paper in Nature magazine journal. It's like the FAC theory, the face armored cubic lattice, is used in all of the heavy elements. And the issue was on May 9th, 2013, and the authors' names were Gaffney and approximately 70 other authors who I'm going to name individually today because they deserve to be honored for their paper on the studies of nuclear pear shapes. And I'll tell you the entire title. And their experiment was done at the CERN facility in Europe. And that's because radon has a 4-day half-life. Once it's created in somebody's basement, in the granite, you're in California, and you have your basement is all dug out, and granite is decaying uranium and things. Radon gas is created from that decay, and then after 4 days, it's only half as dense. So if you can ventilate your cellar, that's a good way to get rid of this concern. Now, the pyramidal cube theory is going to be compared with this experimental information. Now, I think I'm going to take a break for a few seconds and go to the battery connection here so we don't run out. All right, I'm moving cables around here as it looks like my camera is going to run out of battery juice soon. Well, thank you for standing by during this technical difficulty. It seems like the battery now has come back on, so I'm going to use the camera to move around and let you see the Nature article on one of my monitors. Okay, now I brought up a quote from this article. It's from 2013, and I'm going to tell you the title of the article really soon. But the important quote here is about that word at the bottom there, static. Statically, okay? Here's the quote about radon, experimental evidence. For certain combinations of protons and neutrons, there is the theoretical expectation that the shape of nuclei can assume octupole deformation, corresponding to reflection asymmetry or a pear shape in the intrinsic frame, either dynamically, octupole vibrations, or statically, permanent octupole deformations. Now, this is important. I'm trying to establish the static nucleus theory, and experiments already have been speculating it's possible that it's a static shape. So the article this comes from could be showing right now. And here's the shape that they show in from Nature, and this is from a website at ns.ph.liv.ac.uk, _LG papers. Anyway, as you see, it's pear-shaped. Radium and radon are both here, and they don't have as much resolution as what I was trying to show for radon. As you can see in my theoretical geometry, it's much more crisp on the right there, and in the experimental evidence, you could say the magnification is lower. But the actual power, let's see, on my theoretical side, has so much detail around these circles, you could say it's 20 trillion power. And then in the experimental picture, it's maybe 1 trillion or half a trillion power of magnification. So I'm going to bring up the top of this picture here, because that's where they give credit to the authors. And I want to tell you about the authors, because they deserve credit for the historic paper from 2013. All right, it's almost there. It is. Studies of nuclear pear-shapes using accelerated radioactive beams. And it was published in 2013, volume 497 of Nature. And here's the list of the authors. Gaffney, Butler, Scheck, Hayes, Winander, Albers, Baston, Bauer, Blazev, Bonig. These are apparently all from Europe. I saw the listing below of what countries they're from. And Bree, Cedar, Call, Chop, Klein, Kokolios, Davidson. And these are all the authors of this paper in Nature called Studies of Nuclear Pear-Shapes Using Accelerated Radioactive Beams from 2013. And the authors include Mr. Herzon, Gran, Durakin, DeWitt, Hoyce, Jenkins, Kesselut, Conkey, Kowalczyk, Kroll, Kwan, Lutter, Moschner. And these people, as I was saying, come from Europe, and it's listed here. See, they come from the University of Liverpool, Technische Universität Darmstadt, Germany, as well as Finland at the University of Jyväskylä and Helsinki Institute of Physics, as well as other countries such as Spain, the Universidad Autónoma de Madrid, España. So it's a huge effort to use the gas that disappears every 4 days. You can imagine, if you don't even want to touch this stuff, that you have to use vacuums and things of high voltage. And that's why they had people like Marshner, Napurakowski, Pakarinen, Pfeiffer, Radek, Reiter, Reinders, Rigby, Robledo, Rudegier, Sambi, as well as several other people working at CERN and working out octupole deformation of the pear shape at a power of 500 billion. Only in theory can I go beyond that and show you things like the spherical gaps that cause the strong nuclear force. But the experimental evidence was also helped by Stora, Thol, Van Dupen, Vermeulen, von Schmidt, Vula, War, Wimmer, Razek, Lipska, and Wu with the help of Zielinska. So I take it there were some people from outside of Europe also, from the sound of the names in there. And this has been confirming what I say about this element, this nuclear structure. And what I want to tell you about really is listed on this page, in which I'm going to be showing you how these nuclei are structured. Now, the experimental evidence has shown you through Mr. Gaffney et al. That one end is a large end of the nucleus and one end is small. And now here's a close-up of a heavy element like radon. The internal structure has a cube, in my theory, proposed. Cube, 3 by 3 by 3. There's 27 nucleons in there, and they're all colored gray, in this picture because this shape does not depend on which ones are protons. It'll just have to have this shape, and then the protons are assigned so that the exterior has lines of protons allowing electrons to move freely in 2 dimensions. And I'm going to show you a picture of that very soon. Now, at the top is a big pyramid that's dilated there. Now, we all have this theoretical versus experiment, which I've shown you. And this evidence comes with other evidence that the face-armored cubic lattice is the correct theory of nuclear structure. I'm confident of this, and I'm trying to convince 100 million other people in the world that chemists can benefit from this. Now, you can go to my website, pyramidalcube.blogspot.com, or the ferronuclear.blogspot.com. I have 3D models available in the thingiverse.com, and also I have more theoretical physics at impuremath.wordpress.com. So I have been giving proposed theories, but these are not approved by educators. So please consider my theories alongside the alternative. Look at the structure of what you get proposed by other people for all 118 elements. As you search, bring up Bing or a search engine or something and look for images of nuclear structure of iron or radon or anything, and it'll just show you a primitive 1940s hand-drawn illustration of how 57 spheres can pack together into a smooth ball. It's just not possible, but that's what they're trying to show you. Now, I, on the other hand, have given you directly how it's put together in the Journal of Nuclear Physics, March 2019 paper on magnetism from iron's nuclear structure. Now, I also am proposing new theories on electron connecting to proton at the YouTube live streaming Theoretical Physics. My proposals can be accepted or rejected. Use your judgment, please. And I'm here every Monday, Wednesday, and Friday at 20 hours Greenwich Mean Time. But before I wind up, I have quite a bit more to show you about this. And one of them is the 3D modeling that I've been working on for these heavy elements. Now, here is what radon looks like. It is very similar to thorium. Radon is an inert gas, and it's showing lines of protons in white, and the neutrons are in blue. Now, you can obtain a copy of this. Yes, you can get a copy of this from the Thingiverse, and then you could do things like select the whole nucleus and rotate it around. And you could see that the protons form lines of protons because they are connected to electrons. And this is true in a star where fusion's occurring, or in your refrigerator where it's very cold. If there's a nuclear reaction in a cold place, then it is the same as in a very hot place. The protons line up like this. And let me rotate this around a different axis here. All right, so there you go on the Blender picture of radon or francium or thorium. They're all based on this. And the thing is that they are radioactive according to some geometric reasoning. Now, for example, you see that here's polonium is radioactive and radon is radioactive. However, tungsten is not. And the thing is that it's geometrically reasonable. That's in radon here. See these parts sticking out from the edges. Those are vulnerable. These are like polarized. They're darts, like little jet engines, where the front is up at the top, and then it's colliding with things from the top. So it's like a dart going through collisions with little things. And those things will hit these tips on radon there. I'm going to be pointing out this a little more here. So in other words, the top of this model would be going through something, and then these tips down here on the bottom left would be hitting things and getting knocked off, and they'd be broken apart. Let me try and rotate this again. All right, so yeah, it's rotating. Let me try and rotate it on the z-axis. Oh, that's a little better. So anyway, you can see these tips down at the bottom sticking out beyond that big shield on the top. So the big pyramid on top then is an armor that's protecting the rest of the nucleus from destruction. But in this element, you can see that things stick out very far on the left and right here on the bottom, and those are vulnerable to collisions, which is can be seen also on the planning of the theoretical silhouette here. It's sticking out farther. Polonium also, the bottom pyramid is sticking out farther than other ones will be sticking out. But I'm going to be showing you a bit of photography here, which will be some small models I've been using. And I'm just turning the camera around while you're not watching, because it's so abrupt. And now I'm zooming in. I'm ready to show you what I was doing there. Okay, so here's some little models. Small models. All right, I'm going to zoom in on that and take a drink. Yeah, I took a drink, yes. All right, I'm going over to a tiny model of platinum, which is pear-shaped. So that's the big thing about that paper from Butler and his friends there, Gaffney. This is a pear-shaped nucleus based on platinum, which is based on tungsten. Tungsten is a foundation element. Platinum has about 6 more protons here in brown than does the tungsten. Well, let's turn around here a little bit. So you can see it has 6 protons and neutrons in white and brown here. And these are in lines. On the exterior, protons line up with protons, these brown lines here. And the white neutrons are in the exact correct number for the isotopes that are known for platinum. So these have been built up upon those integers, A and Z, the mass number and the atomic number. Uh-oh, I got my fingers in the picture. So I'm going to now back off on the zoom a little bit here. And we see the larger models here where we have the pyramid 4. So tungsten and platinum has pyramid 6, as does radon. And so I just have a little pyramid 4 there on the camera right now. But you can see in the planning stages, I had put together a silhouette for a pyramid 6 on radon. So it's quite a bit bigger, and it would be easy to have integer programs that could create every possible face-armored cubic lattice. And I've tried to be thorough about this and see if I've covered everything. And it appears that, yes, there's nothing likely to be an element outside of the ones that I put on the table, the overall periodic table here. So let's see, I might have a little bit more to talk about here. No, I think that's about it. So I'm going to be winding up the presentation really soon now. I'll be back on Monday. Same time, same Hawaiian weather, 85 degrees today. Thank you very much. Goodbye.